It was 1964. The Beatles were on the Ed Sullivan Show. The Civil Rights Act was signed into law. And in the world of theoretical physics, something strange was taking shape. Two physicists, the Russian cosmologist Igor Novikov in Moscow and the Israeli physicist Yuval Ne'eman in Tel Aviv, were thinking about black holes. They were not working together, but their ideas were converging. Black holes were still a wild concept then, mostly a mathematical curiosity from Einstein's equations. People knew that if you crushed enough matter into a small enough space, gravity would become so strong that nothing, not even light, could escape. This was the black hole, a one-way door in the universe. But Novikov and Neeman asked a different question. What if the equations worked in reverse? In physics, most equations are time-symmetric. They run just as well forward as they do backward. So if there was a one-way door where, things only go in, could there be a one-way door where things only come out? In a paper that year, they seriously explored this idea. They called the object a white hole. It would be the exact opposite of a black hole. It would be a place where matter and energy gushed out, but nothing could ever enter. It would be a source, a cosmic fountain. They even theorized that a white hole could be the exit for matter that fell into a black hole somewhere else, maybe even in another universe. The idea was a perfect mathematical mirror. Matter goes in here, information is seemingly lost, and it comes out there. The universe keeps its balance. This was one of the first serious attempts to grapple with a problem that would haunt physics for the next 60 years. The problem of what happens to the information that falls into a black hole. Does it just vanish? Or does it, as Novikov and Neeman's work suggested, have to go somewhere? Their 1964 speculation opened a door. It suggested that the universe has rules about keeping track of things, rules that are deeper than just matter and energy. It was an early hint that maybe information itself was the thing the universe refused to lose. Number 16, the laws of physics are really just algorithms. The speed of light in a vacuum, 299,792,458 meters per second, is not just a speed limit. It is the exact speed at which causality propagates. Information about an event cannot travel faster than this speed. The fine structure constant, a number approximately equal to 1/137, has no units. It governs the strength of the electromagnetic force. If it were just 4% different, stellar fusion would not produce carbon, and life, as we know, it would not exist. In 1936, Alan Turing described a theoretical machine, the Turing machine, which could simulate any computer algorithm. This abstract concept now forms the basis of every digital computer on Earth, from your phone to the largest supercomputer. The universe seems to follow rules. We call them the laws of physics. We write them down as equations. Gravity pulls things together. The strong nuclear force holds atomic nuclei together. Thermodynamics dictates the flow of heat. But what if these laws are not just descriptions of what happens? What if they are the instructions themselves? This is the idea that the laws of physics are algorithms. An algorithm is just a set of rules to be followed to solve a problem or perform a task. Your computer runs on algorithms. A recipe is an algorithm. So is the process of long division. In this view, the universe is a giant computer. It is not made of silicon chips. It is made of something more fundamental. The hardware could be space-time itself or some deeper quantum substrate. The software is the set of physical laws. The Big Bang was not just an explosion of matter and energy. It was the moment the program started running. Every interaction between particles, every star that forms, every galaxy that collides is the universe executing its code. A particle moving through space is not just following a path of least resistance. It is calculating its next position based on the rules encoded in its properties and the fields it interacts with. This idea comes from a field called digital physics. Thinkers like Edward Fredkin and Stephen Wolfram have pushed this concept. Wolfram in his book A New Kind of Science from 2002, argued that even very simple rules, simple programs, can generate immense complexity. He studied cellular automata, which are simple grids where each cell changes its state based on the state of its neighbors. You know, a few basic rules can lead to patterns that look random, ordered, or as complex as living organisms. Wolfram suggested the universe could be such a system. A few fundamental rules applied over and over since the Big Bang could have generated all the complexity we see today. This changes how we see reality. A particle like an electron is not a tiny solid ball. It is a collection of information. Its properties like charge, spin, and mass are just data. When it interacts with another particle, they are not bouncing off each other. They are exchanging information and updating their states according to a fixed algorithm. The universe becomes a computational process. It is constantly calculating its own future state from its present one. This helps explain some weird things. Why is mathematics so good at describing the universe? Eugene Wigner called this the unreasonable effectiveness of mathematics. If the universe is fundamentally mathematical, if it is running on a kind of code, then it makes sense that our language of code, mathematics, would be the perfect tool to describe it. It also suggests that the universe has a finite resolution. Just like a computer screen is made of pixels, maybe space-time is made of tiny indivisible units below this Planck length, about 1.6 x 10 raised to the power of 35 meters, the concepts of space and distance might not even make sense. The universe would be digital, not analog. It would be grainy at the smallest scales. This would solve many paradoxes in physics involving infinities. But this also leads to a profound question. Who wrote the code? Where did the algorithm come from? This is a question digital physics does not answer. It just reframes our view of what the universe is. It is not a collection of stuff. It is a process, a vast, ongoing computation. The fundamental building block is not matter or energy. It is the instruction, the bit of information, the line of code that says what to do next. Everything else, every particle, planet, and person is just the output of that program. Number 15. Your DNA is a 4 billion-year-old information system. The human genome contains about 3.2 billion base pairs of DNA. If you were to type it all out, it would fill a stack of paperback books 200 feet high. Only about 2% of that DNA codes for proteins. The other 98%, once called junk DNA, is now known to be crucial for regulating when and where genes are turned on and off. The oldest viable DNA ever sequenced came from a 700,000-year-old horse bone found frozen in the Yukon. Life is built on information. At the heart of every living cell is a molecule called deoxyribonucleic acid, or DNA. It is often called the blueprint of life, but it is more accurate to call it a program or a storage device. DNA is a physical manifestation of information. It is a long chain molecule made of 4 basic units called nucleotides adenine A, guanine AG, cytosine C, and thymine T. The sequence of these 4 letters carries the instructions for building and operating an entire organism. The information in DNA is digital. It is not a vague suggestion, it is a precise code. 3 letters of DNA in a row, called a codon, specify a particular amino acid. For example, the sequence GCA tells the cell's machinery to grab an amino acid called alanine. The sequence AGG specifies arginine. Chains of amino acids fold up to become proteins. And proteins do almost everything in the body. They are the enzymes that digest your food, the hemoglobin that carries oxygen in your blood, and the collagen that holds your skin together. It is a pure information processing system. The DNA is the hard drive. Messenger RNA is the RAM carrying a copy of the instructions. The ribosome is the CPU reading the instructions and assembling the product, the protein. This system is ancient. It began about 4 billion years ago with the first life on Earth, and it has been passed down, copied, and modified ever since. The DNA in your cells contains information that has survived for billions of years. It has been tested and refined by natural selection. Every organism is an experiment. The environment poses a problem. DNA provides the information for a potential solution. If the solution works, the organism survives and passes that information on. If it fails, the information is removed from the gene pool. Evolution is a slow, methodical process of information gathering. It is the universe learning about itself through the medium of life. The amount of information is staggering. A single bacterium has about 4 million base pairs of DNA. This is enough information to specify thousands of different proteins. A human has almost 1,000 times more. This information is not just a static list. It is a dynamic program that responds to its environment. Your cells can turn genes on or off in response to signals like hormones, nutrients, or stress. The information in your DNA is not just building you, it is running you, moment to moment. This shows that information is not an abstract concept that only humans care about. It is a physical, causal thing. The sequence of molecules in a strand of DNA has a direct and profound effect on the physical world. It determines whether a cell becomes a neuron or a skin cell, whether a creature has wings or fins. The information comes first. The physical structure follows. This turns the traditional view of the universe on its head. We usually think of matter and energy as primary. We think information is something that complex systems like brains produce, but biology shows us that information is the starting point. Life is what happens when matter becomes organized enough to store, process, and replicate information. It is the universe waking up and starting to write things down. Number 14, time is the processing of information. A single second is officially defined by the radiation from a cesium-133 atom. Specifically, it is the time it takes for 9,192,631,770 cycles of the microwave radiation corresponding to the transition between two energy levels of the atom. Due to general relativity, a clock at the top of Mount Everest runs about 39 microseconds faster per year than a clock at sea level. The earliest known timekeeping devices are from ancient Egypt around 1500 BC in the form of obelisks used as shadow clocks. We experience time as a flow. The past is gone, the future is not yet here, and we live in the fleeting moment of the present. But many physicists argue this is an illusion. The equations of physics, from Newton's laws to Einstein's relativity, do not have a special now. They describe a block universe where past, present, and future all exist equally. Or time is just another dimension, like space. So why do we experience it as a moving arrow? One compelling answer is that time is a measure of information processing. The flow of time we perceive is the universe updating its state. It is the consequence of the universe computing itself. In this view, the present moment is the current state of the cosmic computation. The past is the record of previous states. The future is the set of potential states that have not yet been computed. The arrow of time, the fact that time only seems to move forward, has a simple explanation. Computations are generally irreversible. You can multiply 5 by 7 to get 35. That is a forward computation. But if you only have the number 35, you cannot be certain what two numbers were multiplied to get it. It could have been 5 and 7 or 1 and 35. Information is lost in the reverse direction. Okay? This connects directly to the concept of entropy. The second law of thermodynamics says that the total entropy, or disorder, of a closed system always increases over time. A clean room gets messy. An egg, once scrambled, cannot be unscrambled. This is the physical basis for the arrow of time. But entropy can also be understood in terms of information. In the 1940s, Claude Shannon developed information theory. He defined entropy as a measure of uncertainty or missing information. A high entropy state is one where we have little information about the specific arrangement of its parts. A scrambled egg has higher entropy than an intact one because there are many more ways for the molecules to be mixed up than to be perfectly separated into yolk and white. The universe began in a very low entropy state. The Big Bang was highly ordered. Since then, the universe has been moving towards states of higher entropy. This increase in entropy is the arrow of time. It is also a process of the universe forgetting its initial state. The information is not destroyed, but it is spread out and scrambled, making it harder to recover. So, the passage of time is the physical process of information becoming less concentrated. Every event that happens, every particle interaction is a small computational step. It increases the overall entropy and pushes the no forward. This view makes time less mysterious. It is not a river we are floating down. It is a measure of change. It is the ticking of the cosmic clock, where each tick is an elementary operation, a single processing of a bit of information. This also means that time is not universal. In a region of space-time with more activity, more computational steps are occurring. Time would effectively run faster there. This echoes Einstein's relativity, where gravity, which is related to the density of matter and energy, can warp time. More matter and energy means more potential for interactions, more computation, so information theory and relativity might be two different ways of describing the same underlying reality. The universe is not happening in time. The universe's processing of information is time. Number 13, the universe is fine-tuned with information. The gravitational constant, known as Big G, is 6.67 Folkestone raised to the power of 11 nm squared kg squared. If it were slightly larger, stars would burn out too quickly for life to evolve. If it were slightly smaller, stars would never have ignited in the first place. The cosmological constant, which describes the accelerating expansion of the universe, is incredibly small. If it were much larger, its repulsive force would have ripped the universe apart before galaxies could form. Physicists have calculated its value to be about 10 raised to the power of 120 times smaller than theory predicts it should be. This is the most inaccurate prediction in the history of science. In 2000, physicist and astronomer Martin Rees wrote a book called Just Six Numbers, arguing that 6 fundamental physical constants must be set to very precise values for the universe to be habitable. The universe seems to be balanced on a knife's edge. A handful of numbers, the fundamental constants of nature, have values that appear to be exquisitely fine-tuned to allow for the existence of complex structures like stars, planets, and life. If you were to change these numbers even slightly, the universe would be a sterile, empty place. This is called the fine-tuning problem. Take the strength of the strong nuclear force. This is the force that binds protons and neutrons together in an atom's nucleus. If it were just 2% weaker, like protons could not stick together. The only element would be hydrogen. There would be no chemistry, no stars beyond simple hydrogen gas balls, no life. If it were just 2% stronger, protons would bind so tightly that all the hydrogen in the early universe would have fused into heavier elements. There would be no hydrogen left to fuel stars like our sun, and no water H2O. This looks like an incredible coincidence. Why do these numbers have the specific values they do? There are a few possible explanations. One is pure luck. We just happen to live in a universe where the numbers are right. This is unsatisfying to many scientists. Another possibility is a multiverse. Maybe there are countless universes, each with different values for these constants. We, of course, find ourselves in one of the few that can support life because we could not exist to observe the others. This is called the anthropic principle, but there is a third way to look at it. The fine-tuning is not a coincidence. It is information. The values of these constants are information that is encoded into the fabric of the universe from the very beginning. It is as if the universe was born with a specific set of parameters, a recipe for making life possible. These numbers are not random. They are the foundational data on which the entire cosmic program runs. Where did this information come from? That is the big question. But thinking of it as information changes the problem. Instead of asking why is gravity so weak, we can ask what process encoded the value of the gravitational constant. It frames the universe not as a brute fact, but as a system that carries specific, meaningful data. This data has a tangible effect. It dictates the entire history and structure of the cosmos. This suggests that information is not just something we use to describe the universe. It is something the universe uses to define itself. The constants are not just numbers we measure. They are bits of information that have been present since the Big Bang. They are the seed of complexity. Without this initial, highly specific information, the universe would have remained a simple, uniform soup of particles. The fine-tuning problem is evidence that information is not an emergent property of complex systems. It is the foundational property that allows complex systems to emerge in the first place. It is the operating system of reality. Number 12, quantum entanglement, is pure information connection. In 1964, physicist John Bell devised a mathematical theorem, Bell's theorem, that could experimentally test whether quantum mechanics or local realism, Einstein's view, was correct. Every experiment conducted since the 1970s, most notably by Alain Aspect in 1982, has confirmed quantum mechanics and violated Bell's theorem. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their pioneering experiments with entangled photons. The scientists have successfully entangled particles separated by over 1,200 kilometers. Quantum entanglement is one of the strangest and most profound features of reality. Einstein called it spooky action at a distance. It works like this. You can create a pair of particles, like photons, that are linked in a special way. Their properties, like spin, are correlated. For example, if one particle has a spin up, you will always find the other has a spin down, and vice versa. The strange part is that neither particle has a definite spin until it is measured. They exist in a superposition of both states. But the moment you measure one, you instantly know the state of the other, no matter how far apart they are. If one particle is on Earth and the other is on Mars, measuring the Earth particle to be spin up instantly forces the Mars particle to be spin down. This seems to violate the cosmic speed limit, the speed of light. Information about the measurement on Earth seems to travel to Mars instantaneously. However, this spooky connection cannot be used to send a message faster than light. You cannot control the outcome of your measurement. You might get spin up or spin down at random. The person on Mars will also see a random sequence of spins. It is only later, when you compare your two sets of measurements, that you see the perfect anti-correlation. So what is being shared between these particles? It is not a force. It is not energy. It is information. Entanglement is a purely informational link. The two particles are not separate entities that communicate. They are best described as a single system, described by a single piece of information, a single wave function. Measuring one part of the system gives you information about the whole system. The distance between them is irrelevant. This suggests that our classical view of space and separation is wrong, at least at the quantum level. Two entangled particles are, in an informational sense, in the same place. The information that defines them is non-local. It is not confined to a single point in space. This is a radical idea. It means the universe is connected in ways we do not intuitively grasp. This supports the idea that information is more fundamental than space. Space might be an emergent property of the relationships between bits of information. Think of the internet. Two computers can be linked, sharing information. The physical distance between them is less important than the informational connection. In quantum entanglement, the universe shows us that this is not just a metaphor. It is a physical reality. The information is not in the particles. The particles are the information. Their existence as a correlated pair is a fact, a bit of relational information. When we measure them, we are not discovering a pre-existing property. We are interacting with the system in a way that forces it to resolve into a definite state, a classical bit of information up or down. But the underlying reality is the quantum information, the state of superposition and entanglement. This quantum information is the raw material from which our classical local reality is built. The universe is not a collection of separate objects moving through space. It is a web of informational relationships. The entanglement is the clearest glimpse we have of that web. Number 11, entropy is just missing information. In 1877, physicist Ludwig Boltzmann proposed a formula, S equals K log W, which is now engraved on his tombstone. It connects entropy S to the number of possible microscopic arrangements W of a system. This was the first time a macroscopic property, like entropy, was linked to the statistical behavior of microscopic parts. In 1948, Claude Shannon, working at Bell Labs on communication theory, independently developed a nearly identical formula for informational entropy. He was trying to figure out how to quantify the amount of information in a message. The physicist John von Neumann reportedly told Shannon to call his new quantity entropy, because nobody knows what entropy is. So in a debate, you will always have the advantage. We usually think of entropy as a measure of disorder or randomness. A messy room has high entropy. A tidy room has low entropy. The second law of thermodynamics says that entropy always increases in an isolated system. This is why a hot cup of coffee cools down and a broken glass never reassembles itself. It is the law that gives time its arrow. But what if entropy is not about disorder at all? What if it is about information? The information theory perspective, started by Claude Shannon, redefines entropy as a measure of our ignorance about a system. It is the amount of missing information needed to specify the exact state of that system. Imagine a deck of cards. If the cards are perfectly ordered from ace to king for each suit, the deck has very low entropy. You know exactly where every card is. You have complete information. Now shuffle the deck. It now has high entropy. This is not because it is disordered. It is because you no longer know the position of any given card. There are a huge number of possible arrangements about 8x10 raised to the power of 67, and you do not know which one you have. The entropy is high because your information is low. The amount of entropy is precisely the amount of information you would need to be given to know the exact sequence of the shuffled deck. This applies to physical systems too. A container of gas has high entropy. The gas molecules are bouncing around randomly. We know the gas's temperature and pressure, which are average properties, but we do not know the exact position and velocity of every single molecule. The entropy of the gas is a measure of that missing microscopic information. A crystal, on the other hand, has low entropy. The atoms are locked in a regular, predictable lattice. Knowing the position of a few atoms allows you to predict the position of all the others. We have much more information about the microscopic state. The second law of thermodynamics in this light is not a law about things getting messier. It is a law about information becoming less accessible. When the coffee cools down, the energy does not disappear. It spreads out into the surrounding air. The total energy is the same, but the information about where the high energy molecules are in the cup has been lost as they mix with the low energy molecules of the air. The information has been diluted. An unscrambled egg becomes a scrambled egg. The number of possible ways the molecules can be arranged increases dramatically. The system moves from a state we know a lot about, yolk here, white there, to a state we know very little about. They are all mixed up. This means that one of the most fundamental laws of physics is really a law about information. It is not matter or energy that drives the universe forward, but the relentless tendency for information to spread out and become harder to track. This links the abstract world of bits and data directly to the physical processes of heat, work, and decay. The universe is not just moving towards thermal equilibrium, a state of uniform temperature. It is moving towards informational equilibrium, a state of maximum missing information. This reframes our place in the cosmos. We, as living beings, are low-entropy systems. We are pockets of immense order and information. Life is a constant struggle against the second law, a temporary victory of information over ignorance. Number 10, the universe could be a simulation. The Planck length is the smallest possible unit of distance, about 1.6 x 10 raised to the power of 35 meters. At this scale, our current laws of physics break down. If the universe is a computer simulation, this could be the pixel size of reality. The processing power required to simulate the entire visible universe down to the quantum level is estimated to be around 10 raised to the power of 122 operations per second. Even the world's fastest supercomputer, as of 2023, can only perform about 10 raised to the power of 18 operations per second. In 2003, Oxford philosopher Nick Bostrom published a paper arguing that we are almost certainly living in a computer simulation. His argument is based on probability and the assumption that a technologically mature civilization would be able to create such simulations. This is the simulation hypothesis. It proposes that our reality, everything we see and experience, is not the fundamental reality. It is an artificial, simulated reality created by a more advanced intelligence. This idea has moved from science fiction to a topic of serious academic debate. It is a modern version of ancient philosophical questions about the nature of reality. But it is grounded in the language of information and computation. If the universe is a simulation, then it is fundamentally made of information. The underlying reality is not particles and fields. It is code and data being processed by some vast computer. The laws of physics are the algorithms of the simulation. The fundamental constants are parameters set in the code. The speed of light is the processing speed of the simulation's Q. The pixelated nature of space-time at the Planck scale is the resolution of the simulation grid. This idea provides potential answers to some deep mysteries. The unreasonable effectiveness of mathematics in describing the universe is no longer unreasonable. If the universe is based on code, it makes sense that the language of logic and code, mathematics, would describe it perfectly. The fine-tuning of the physical constants might not be a cosmic coincidence. It could be that the simulators simply dialed in the parameters needed to create an interesting universe with complex structures and life. Quantum mechanics, with its weirdness, also fits nicely into this picture. A particle's properties are not definite until measured. That sounds like a simulation optimizing its resources. Why render the detailed properties of a particle if no one is looking at it? The particle exists as a set of probabilities until an observation is made. At that point, the simulation calculates a definite outcome and renders it for the observer. This is similar to how video games work. The game engine only renders the part of the world the player is currently looking at to save processing power. The rest of the world exists only as data until it needs to be displayed. Quantum entanglement, the spooky action at a distance, could just be 2 points in the simulation that reference the same variable in the code. Changing one instantly changes the other because they are not two separate things. They are two manifestations of the same underlying data, but how could we ever test this? And physicists have proposed some ideas. One is to look for tiny glitches or artifacts in the simulation. For example, high-energy cosmic rays might not behave exactly as our physical laws predict if they are interacting with the grid of the simulation. Another idea is that the laws of physics might not be perfectly constant. The simulators might be tweaking the code or performing maintenance, leading to tiny measurable changes in physical constants over time. So far, we have found no such evidence. The simulation hypothesis is impossible to disprove. Any evidence against it could simply be part of the simulation. but it is a powerful thought experiment. It forces us to take seriously the idea that information is the primary reality. It suggests that our entire universe of matter, energy, space, and time could be just the output of a program. We might not be physical beings in a physical world. We might be informational patterns running on a cosmic hard drive. Number 9, the mathematical universe is made of information. In 1931, Kurt Gödel published his incompleteness theorems. They showed that in any consistent formal system powerful enough to describe basic arithmetic, there will always be true statements that cannot be proven within that system. This put fundamental limits on what mathematics can prove. The Mandelbrot set, a famous fractal, is generated by a very simple equation Zooplon equals Zooplon raised to the power of 2 plus c, yet it contains infinite complexity and detail. It is a mathematical object that seems to have an existence independent of human minds. The number pi p, the ratio of a circle's circumference to its diameter, has been calculated to over 100 trillion digits. Its digits appear to be completely random, yet they are rigidly determined by its mathematical definition. Where does mathematics exist? We use it to describe the universe, but the mathematical objects themselves, numbers, shapes, equations, do not seem to be physical. The number 3 is not a physical thing. You can have 3 apples, but the concept of 3 itself is abstract. Plato believed that these mathematical forms existed in a separate ideal realm. The mathematical universe hypothesis MUH, proposed by physicist Max Tegmark, takes this idea to its ultimate conclusion. It states that our physical universe is not just described by mathematics, it is a mathematical structure. There is no distinction. Everything in the universe, including us, is part of a giant mathematical object. And every mathematical structure that exists also corresponds to a physical universe. This is a radical form of Platonism. In this view, the fundamental building block of reality is not a particle or a string. It is a number, a set, a mathematical relation. These things are pure information. The number 5 is a piece of information. The Pythagorean theorem is a piece of information. The MUH says that reality is constructed entirely from such abstract informational entities. This hypothesis offers a solution to the ultimate why question in physics: why these laws and not others? In the MUH, all possible mathematical structures exist. Our universe corresponds to one specific mathematical structure, one with the right properties to allow for self-aware substructures like us to emerge and observe it. We find ourselves in this particular mathematical structure because we could not exist in others. This also explains why mathematics is so effective at describing our reality. It is not a tool we invented. It is the very fabric of the thing we are studying. We are not discovering physical laws and then creating math to model them. We are uncovering the underlying mathematical code of our own existence. But what does it mean for something to be a mathematical structure? It is a set of abstract entities and the relations between them. For example, the integers and the operations of addition and subtraction form a mathematical structure. Tegmark argues that a complex enough structure could contain self-aware substructures that perceive themselves as living in a physical world. Our experience of a rich physical reality would be a user illusion generated by the complex relationships within the mathematical structure. This is perhaps the most extreme version of the information as fundamental idea. It strips away everything else. There is no physical stuff. There is only the pure, timeless, abstract information embodied in mathematical relationships. A particle is not a thing. It is a set of numbers, mass, charge, spin, and the equations relations that govern how those numbers change. Space-time is not a fabric, it is a geometric structure, a set of points, and the distance relations between them. The challenge for this hypothesis is to explain how a static, abstract mathematical object can give rise to our experience of a dynamic, evolving universe with the passage of time. Tegmark suggests that a self-aware substructure would perceive time by virtue of its position within the larger timeless mathematical structure. It is a difficult concept to grasp, but it provides a potential framework where information in its purest, most abstract form as mathematics is not just a building block of the universe. It is the universe itself. Number 8, consciousness is integrated information. The human brain contains about 86 billion neurons. Each neuron can form connections or synapses with thousands of other neurons, creating a network with an estimated 100 trillion connections. The octopus brain is incredibly strange. It has about 500 million neurons, but more than half of them are in its arms. Each arm can act semi-independently, able to taste, touch, and move on its own. In 1994, philosopher David Chalmers coined the term the hard problem of consciousness to describe the mystery of why we have subjective, qualitative experiences like the redness of red or the feeling of pain. What is consciousness? We all know what it is to be conscious. It is the feeling of being me, the experience of sights, sounds, thoughts, and emotions. But for centuries, science and philosophy have struggled to explain how a physical object like the brain, a 3-pound lump of fatty tissue, can produce this inner subjective world. The integrated information theory 2T, developed by neuroscientist and psychiatrist Giulio Tononi, proposes a bold answer. It says that consciousness is integrated information. It is not something the brain produces. It is a fundamental property of certain kinds of systems. IIT starts with a few key observations about consciousness. First, every conscious experience is incredibly informative. When you open your eyes, you are instantly aware of a vast, detailed scene. You do not just see a room. You see a specific room with specific colors, shapes, and objects in a specific arrangement. This is a huge amount of information. Second, this information is integrated. You do not experience the color red separately from the shape of a ball. You experience an integrated red ball. All the different parts of your experience are bound together into a single, unified whole. TYT proposes to measure this. It defines a quantity called phi-pH, which represents the amount of integrated information in a system. A system has high phi if it has many possible states, it is informative, and if its parts are highly interconnected and interdependent, it is integrated. You cannot break the system down into independent components without losing information. According to IIT, any system with a phi value greater than 0 has some degree of consciousness. A system with a high phi, like a human brain, is highly conscious. A system with a low phi, like a simple thermostat, might have a tiny flicker of consciousness, but so little we would not recognize it. A digital computer, even a very powerful one, would have a low phi according to the theory. This is because its architecture is not highly integrated. You can analyze the CPU separately from the RAM, and the hard drive separately from the monitor. Its parts are not as deeply causally intertwined as the neurons in a brain. This theory has some startling implications. It means consciousness is not limited to biological brains. An artificial intelligence, if built with the right kind of integrated architecture, could be conscious. It also means consciousness could be a matter of degree, existing on a spectrum across the animal kingdom and perhaps even in simpler systems. It also suggests that consciousness can be turned off. During dreamless sleep or anesthesia, the brain's connectivity changes. The integration between different brain regions breaks down. The brain is still active, but the information is no longer integrated. As phi drops and consciousness fades, most importantly, IIT frames consciousness as a phenomenon of information. It is not about the specific material a system is made of, whether it is carbon-based neurons or silicon chips. It is about the structure of the information and how it is processed. Consciousness is what it feels like to be a system with a particular kind of complex, integrated informational structure. This places information at the very core of our being. Our subjective experience, the thing that is most real to us, is a direct manifestation of the way information is organized and woven together inside our heads. It suggests the universe has a potential for experience built into its fabric, a potential that is realized whenever information becomes sufficiently integrated. Number 7, constructor theory defines reality by information. The laws of physics, like Newton's laws of motion, are typically expressed in terms of what happens. They describe the trajectory of objects over time. They do not explicitly state what is possible and what is impossible. In 1959, Richard Feynman gave a famous lecture titled "There's Plenty of Room at the Bottom, Predicting the Field of Nanotechnology." He was thinking not just about what nature does, but what it could be made to do. Quantum computers, first proposed in the 1980s, are a prime example. They are not something that exists in nature. They are a possible transformation of matter allowed by the laws of quantum mechanics that we are trying to build. Our current laws of physics have a problem. They are good at predicting the future if you know the initial conditions, but they are not good at explaining the big picture principles that seem to span all of physics. Principles like the conservation of energy, the second law of thermodynamics, and the nature of information itself. These are not equations of motion. They are statements about what transformations are possible and which are impossible. Constructor theory, developed by physicist David Deutsch at the University of Oxford, is a radical new approach to physics. It proposes to rebuild all of physics on a new foundation. Instead of describing reality in terms of states and trajectories, it describes it in terms of which transformations are possible and which are impossible. The fundamental entity in constructor theory is the constructor. A constructor is anything that can cause a given transformation without undergoing any net change itself. A catalyst in a chemical reaction is a simple example. It facilitates the reaction, but remains unchanged at the end. A 3D printer is a more complex constructor. It can take a raw material and a design and transform it into a specific object. The core idea is to express all physical laws as statements about constructors. For example, the law of conservation of energy would be stated as, "It is impossible to construct a perpetual motion machine." This seems like a simple rewording, but it has profound consequences. It shifts the focus from what happens to what can be made to happen. This is where information comes in. In constructor theory, information takes center stage, and Deutsch defines information not in terms of probability or Shannon entropy, but in terms of physical possibility. A system contains information if it is possible to create a copy of it. Knowledge is a type of information that can cause things to happen. For example, the DNA sequence for an enzyme is knowledge. It is a piece of information that, when put into the constructor called a ribosome, can cause the construction of that enzyme. This framework allows physics to talk about things it has struggled with, like life and knowledge. A living organism is a system that contains knowledge in its DNA about how to construct copies of itself. Evolution is a process that creates new knowledge. This makes information a physical quantity defined by its ability to be copied and to cause transformation. Constructor theory claims that the principle that information can be copied is a fundamental law of nature. It calls this the constructor theory of information. It also provides a physical basis for the distinction between information and randomness. A random sequence of letters is not information because there is no simple constructor that could reliably reproduce it. The text of a book is information because a constructor like a printing press or a person can create copies. This approach aims to unify physics. It tries to explain why principles like thermodynamics, computation, and life all seem to exist. They are all consequences of the underlying logic of possible and impossible transformations. The universe is not just a collection of particles following paths, it is a medium in which certain things can be built and certain knowledge can be created. The fundamental building blocks are not particles, they are the possible tasks, the set of all transformations that can be performed. And at the heart of this is information, the stuff that can be copied and used to direct those transformations. Your reality is defined not by what it is, but by what it can do. and what it can do is determined by the information it contains. Number 6, the black hole information paradox demands it. In 1974, Stephen Hawking calculated that black holes are not completely black. Due to quantum effects near the event horizon, they should slowly radiate energy, now called Hawking radiation. This radiation has a thermal spectrum, meaning it appears to be random and contains no information about what fell into the black hole. A black hole with the mass of our sun would take an unimaginable 10 raised to the power of 67 years to evaporate completely. A black hole with the mass of a car would evaporate in less than a second. According to general relativity, once something crosses the event horizon of a black hole, it can never get out. It is crushed into a singularity, a point of infinite density where the laws of physics break down. This leads to a massive problem, one of the deepest in modern physics. It is called the black hole information paradox. The problem is this quantum mechanics, one of the pillars of modern physics, has a strict rule. Information can never be destroyed. It can be scrambled, hidden, or rearranged, but the total amount of information in a closed system must always be conserved. This is called unitarity. So what happens when something with information, like a book, falls into a black hole? According to general relativity, the book is crushed at the singularity and its information is lost forever from our universe. According to Stephen Hawking's 1974 calculation, the black hole then slowly evaporates, emitting only random thermal radiation. This radiation carries no information about the book. When the black hole is completely gone, the information that made up the book seems to have vanished from the universe. This creates a fundamental conflict between general relativity and quantum mechanics. One says information is lost, the other says it is conserved. For decades, physicists have been trying to solve this paradox. Most believe that quantum mechanics must be right, and the information must somehow get out. But how? This paradox forces us to consider information as a fundamental physical quantity that must be accounted for. It is not just an abstract concept, it has to be as real and as conserved as energy. The universe must have a bookkeeping system that never loses a single bit. Several potential solutions have been proposed, and all of them treat information in a radical way. One idea is that the information is not lost, but is stored on the surface of the black hole, on its event horizon. This is a key idea behind the holographic principle. Another idea is that the information escapes, subtly encoded in the Hawking radiation itself. This would mean Hawking's original calculation was incomplete. There must be tiny, non-random correlations in the radiation that carry the information. This would require new physics to explain. A third, more extreme idea is that the information goes into a Bobby universe that buds off from our own. A fourth is the concept of a firewall, a high-energy region at the event horizon that destroys anything falling in, releasing its information back out. No matter which solution turns out to be correct, the paradox itself tells us something profound. The universe seems to care deeply about information. The laws of physics are structured in such a way that the destruction of information is forbidden. This suggests that information is not just a property of matter, it might be the other way around. Matter might be a carrier, a vessel, for the more fundamental quantity of information. The black hole information paradox is the universe's way of showing us this. It presents us with an impossible situation, forcing us to re-evaluate our basic assumptions. And the assumption that seems most likely to be wrong is that information is secondary to matter and energy. The paradox insists that information is primary. Number 5, the holographic principle puts reality on the boundary. The Bekenstein bound, formulated by Jacob Bekenstein in 1972, sets an upper limit on the amount of information that can be contained within a given region of space. Surprisingly, this limit is not proportional to the volume of the region, but to the area of its surface. A gram of matter contains roughly 10 raised to the power of 23 atoms. A USB stick can hold about 10 raised to the power of 23 bits of information. A black hole with the mass of a gram would have an entropy, or information content, of about 10 raised to the power of 37 bits, far more than the matter that formed it. In 1997, physicist Juan Maldacena proposed a concrete mathematical example of the holographic principle called the ADS-CFT correspondence. It has become one of the most cited papers in the history of theoretical physics. This is one of the most mind-bending ideas to come out of theoretical physics. The holographic principle suggests that our three-dimensional reality might be an illusion. It proposes that all the information contained in a volume of space can be described by a theory that lives on the boundary of that region. It is like a hologram. A hologram is a two-dimensional photographic plate that, when illuminated with a laser, produces a full three-dimensional image. All the information for the 3D image is encoded on the 2D surface. The holographic principle suggests the entire universe might work this way. Everything that happens in the 3D space we experience could be a holographic projection of physical processes happening on a distant 2D surface. The real universe would be the lower dimensional boundary. We are the projection. This idea did not come from science fiction, it came from the study of black holes. When Jacob Bekenstein and Stephen Hawking studied the entropy of black holes, they found a strange result. The entropy of a black hole, which is a measure of its information content, was not proportional to its volume, as you would expect. It was proportional to the surface area of its event horizon, the two-dimensional boundary from which nothing can escape. This was a huge clue. It was as if all the information about the 3D stuff that had fallen into the black hole was somehow stored on its 2D surface. Physicist Gerard Hooft and Leonard Susskind took this idea and ran with it. They proposed that this might not just be a property of black holes, but a property of the entire universe. The maximum amount of information you can cram into any region of space is determined by the area of that region's boundary, not its volume. If this is true, it means that our world is fundamentally informational. The 3D world we see is not the basic reality. It is an emergent, effective description of a more fundamental reality that has fewer dimensions. The fundamental building blocks are bits of information on some distant cosmic boundary. The interactions between these bits give rise to the illusion of space, time, gravity, and matter. This has profound implications. It suggests that space itself is not fundamental. It is constructed from the relationships between bits of information. 2 points may seem far apart in our 3D world, but in the underlying 2D description, their informational bits might be closely linked. This could explain non-locality and quantum entanglement. Two entangled particles, no matter how far apart in 3D space, might be next to each other on the holographic boundary. The holographic principle provides a potential solution to the black hole information paradox. The information that falls into a black hole is not lost. It is scrambled and stored on the event horizon. When the black hole evaporates, this information is returned to the universe via the Hawking radiation. This is a radical shift in our view of the cosmos. We are used to thinking of the world as being made of tiny particles moving around in a 3D container called space. The holographic principle says this is the wrong way to look at it. The world is made of information, and that information lives on a surface, a boundary. The 3D world we inhabit is a complex and convincing projection, a hologram generated by bits of information. The most fundamental building block of the universe is not the atom. It is the bit, stored on the edge of reality. Number 4, quantum information is the ultimate substance. A classical bit of information is either a 0 or a 1. A quantum bit or qubit can be a 0, a 1, or a superposition of both at the same time. This is what gives quantum computers their potential power. A 300 qubit quantum computer could, in theory, perform more calculations simultaneously than there are atoms in the visible universe. In 2019, Google claimed to have achieved quantum supremacy with its 53-qubit Sycamore processor. It performed a specific calculation in 200 seconds that would have taken the world's most powerful classical supercomputer an estimated 10,000 years. We are used to thinking of information in classical terms. A switch is either on or off. A statement is either true or false. This is the world of bits, of zeros and ones. But the universe, at its most fundamental level, does not work this way. It works according to the rules of quantum mechanics, and the information in the quantum world is very different. It is carried by qubits. A qubit is the basic unit of quantum information. Unlike a classical bit, a qubit can exist in a continuous range of states between 0 and 1. This is called superposition. Think of a spinning coin. While it is spinning, it is neither heads nor tails. It is in a superposition of both. Only when it lands, when it is measured, does it take on a definite value. A qubit is like that spinning coin. It holds more information than a classical bit because it contains the potential for both outcomes. Furthermore, qubits can be entangled. This means the state of one qubit can be linked to the state of another, no matter how far apart they are. This creates correlations that are impossible in the classical world. This interconnectedness allows for information to be processed in a fundamentally new way. The idea that quantum information is the ultimate substance of the universe suggests that the weirdness of quantum mechanics is not a strange property of matter. It is a strange property of information itself. The world is built not from classical bits, but from these more powerful and mysterious qubits. In this view, every particle in the universe is a physical manifestation of a qubit or a set of qubits. An electron's spin is not a tiny ball spinning up or down. It is a qubit. Its state is a superposition of up and down until it is measured. The interactions between particles are exchanges of quantum information. The laws of physics are the rules that govern how this quantum information evolves. This resolves many conceptual problems. The wave-particle duality, the fact that a particle like an electron can act like both a spread-out wave and a localized particle, makes sense. It is a wave of information, a wave of possibilities. When you measure it, the wave collapses and the information becomes definite at a single point. The entire universe can be seen as a giant quantum computer. It is constantly processing qubits. The Big Bang was the initial state of this computer. The evolution of the universe is the computation it is performing. Every event is a step in the quantum algorithm. This is not just a philosophical idea. It is the basis for the field of quantum computing. We are learning to build machines that harness the power of quantum information. By manipulating qubits, these machines can solve problems that are intractable for even the most powerful classical computers. We are learning to speak the universe's native language. This perspective suggests that reality is a vast, interconnected quantum information network. The things we call particles are just localized excitations of this network. The things we call forces are the interactions between them. The thing we call space is the geometry of the network's connections. The fundamental reality is the qubit. It is the raw material from which everything else is made. The universe is not a machine made of matter. It is a computation made of quantum information. Number 3, digital physics says the universe is a computer. In the 17th century, Gottfried Wilhelm Leibniz, the co-inventor of calculus, developed the binary number system using only 0s and 1s, which is the foundation of all modern computers. He also mused that the universe might be a kind of machine governed by logical principles. In 1969, Konrad Zuse, who built one of the first programmable computers in the 1930s, published a book titled Calculating Space. In it, he proposed that the entire universe is a cellular automaton, a giant grid of cells computing its own evolution. The physicist John Archibald Wheeler was famous for coining phrases. In 1989, he came up with "it from bit," which became the central slogan for digital physics. This is the most straightforward version of the information as fundamental idea. It is the thesis that the universe is, at its core, a giant digital computer. It is not like a computer. It is one. Everything in the universe, from the smallest particle to the largest galaxy cluster, is the result of a computational process. The hardware of this computer is the fundamental fabric of reality, whatever that may be. It could be a grid of cells at the Planck scale. Each cell can be in a specific state, represented by a number or a bit. The software is the set of rules, the physical laws that determine how the state of each cell changes based on the states of its neighbors. Time is the ticking of the computer's clock. With each tick, the entire universe calculates its next state. In this view, a particle is not a solid object. It is a pattern of information moving across the grid. A particle collision is what happens when two of these patterns interact, and their underlying bits are updated according to the rules. The rich, complex world we see is an emergent phenomenon. It arises from the interaction of billions upon billions of simple bits, all following a simple program. This is the idea behind Stephen Wolfram's A New Kind of Science. He showed that even incredibly simple programs can generate behavior that is as complex and unpredictable as anything we see in nature. This digital model of the universe has several attractive features. It solves the problem of infinities that plagues physics. If space is discrete, made of pixels, then you can never have an infinitely small distance or an infinitely large energy in a finite volume. Everything is finite and countable. It also suggests that the laws of physics might be discoverable. They are not some transcendent, unknowable truth. They are an algorithm. If we are clever enough, we might be able to figure out the code. This idea also leads to some testable predictions. If spacetime is a discrete grid, there might be subtle effects. For example, the speed of light might not be exactly the same for photons of all energies. A very high-energy photon might see the grid structure of space differently than a low-energy one. We are currently conducting experiments to look for such tiny variations. Of course, this raises the ultimate question: if the universe is a computer, who built it? Who wrote the program? Digital physics does not provide an answer. The program could be a brute fact of existence. Or it could imply a programmer. This is where physics touches on philosophy and metaphysics. But regardless of the origin, the core idea is powerful. It replaces the old metaphor of the universe as a clockwork machine with a new, more powerful one, the universe as a programmable computer. It asserts that the most fundamental level of reality is not matter or energy, but the bit of information. The universe is not made of its. It is made of bits. And the its, the physical world we experience, are the output of the cosmic computation. Number 2. Life is what happens when information learns. A single E. coli bacterium with a genome of about 4.6 million base pairs can replicate itself in about 20 minutes under ideal conditions. This means one bacterium can become over 1 billion in about 10 hours. The process of protein folding is an information problem. A chain of amino acids, the primary information from DNA, must fold into a precise 3D shape to function. Misfolded proteins are responsible for diseases like Alzheimer's and Parkinson's. The RNA world hypothesis suggests that before DNA and proteins, life was based on RNA. RNA can both store information like DNA and catalyze chemical reactions like a protein, making it a possible all-in-one starting point for life. We often see life as a special, almost magical phenomenon, separate from the lifeless world of rocks and stars. But from an informational perspective, life is a natural, perhaps even inevitable, consequence of the laws of physics. Life is what happens when information finds a way to preserve and replicate itself. The story begins with simple chemistry. In the early Earth's oceans, there were countless molecules bumping into each other. Some of these molecules, by pure chance, were able to act as catalysts, encouraging the formation of copies of themselves. This was the beginning of replication. This was the moment that information started to matter. A molecule was no longer just a random arrangement of atoms. It was a pattern, an instruction: make more of me. This simple act of replication started a new game, the game of evolution. The copies were not always perfect. Random errors or mutations would occur. Most of these errors would create molecules that were worse at replicating. They would die out. But very rarely, a mutation would create a molecule that was slightly better at replicating. Maybe it was more stable, or it was faster at making copies. This new improved information would spread. This is natural selection, but applied to information itself. It is a learning process. The environment sets the challenges. The information, the sequence of the replicating molecule provides the attempted solutions. Over millions of years, this process of trial and error built up vast stores of information. Molecules teamed up. They built protective membranes around themselves, creating the first cells. They developed ways to store the master copy of the information more safely in the more stable molecule of DNA. They developed machinery, proteins, to read that information and carry out its instructions. Every living organism is a physical embodiment of the information that has been accumulated by its ancestors over billions of years. Your DNA is a library containing the winning strategies from an unbroken line of survivors stretching back to the first replicator. It contains the information for how to build a heart, how to digest sugar, how to fight off a virus. This view demystifies life. It is not about some special spark. It is about the physics of information. A system is alive if it can store information, replicate it, and evolve to create new information. Life is a physical process that is organized around the preservation and propagation of information. This suggests that the universe has a tendency to generate complexity and knowledge. The same laws of physics that govern the stars also allow for the emergence of systems that can learn. Life is the universe's way of developing a memory. It is the universe writing down what works. In this context, we humans are a remarkable step in this process. We have developed a new way of storing and transmitting information culture. We have language, writing, science, and the internet. Information is no longer just passed down through genes. It is passed down through ideas. The pace of learning has accelerated dramatically. We are now actively trying to understand the universe's code. This reframes our existence. We are not just a random accident. We are the current cutting edge of a 4 billion-year-old information gathering process. We are what happens when information becomes complex enough to start asking questions about itself. The fundamental building block is the heritable bit of information, the replicator. And life is the machine it builds to protect and copy itself. Number 1, John Wheeler's It from Bit is the foundation. In the 1950s, physicist John Archibald Wheeler was a key figure in the development of the hydrogen bomb. Later in his life, he turned to more foundational questions in physics, working on quantum gravity and black holes. He was the one who coined the terms black hole and wormhole. Wheeler was famous for his really big questions, which he would write on the blackboard to provoke his students. One such question was, how come the quantum? He was asking why the world has its strange quantum nature. In a 1989 essay titled Information Physics Quantum: The Search for Links, Wheeler laid out his it from bit doctrine. At the heart of all these ideas is a simple, powerful phrase, it from bit. Coined by the brilliant and eccentric physicist John Archibald Wheeler, it encapsulates a revolutionary proposal for the nature of reality. It suggests that every physical thing, every particle, every field of force, even space-time itself, derives its existence entirely from bits, from information. The traditional view of physics is bit from it. We start with a physical world of particles and forces. Then complex systems like brains emerge, and these systems can process information, the bits. In this view, information is secondary. It is something that matter does. Wheeler flipped this on its head. He proposed that the information is primary, the physical world is secondary, the universe is not made of things. It is made of answers to yes or no questions. It is made of bits. How does this work? Wheeler pointed to the strange nature of quantum mechanics. In the quantum world, a particle's properties are often not defined until you measure them. An electron does not have a definite position until you ask it, "Are you here?" through an experiment. The act of observation, the act of asking a question and getting an answer, a bit of information, seems to play a crucial role in creating the reality we perceive. Wheeler imagined the universe as a kind of participatory system. The universe and the observers within it are part of a closed loop. The universe gives rise to observers. The observers, through their measurements and questions, give rise to the tangible reality of the universe. Our acts of observation are not passive. They are acts of creation, collapsing a cloud of possibilities into a concrete reality. Each measurement adds one more it to the world, one more bit of reality chiseled out of the quantum fog. This is not just a philosophical stance. It suggests that the laws of physics are ultimately about information. We should not be looking for the ultimate particle. We should be looking for the ultimate informational principle that explains why the world is the way it is. The it from bit doctrine is the common thread that runs through all the other ideas. For digital physics is the idea that the bits are processed like a computer. The holographic principle is the idea that the bits live on a boundary. Quantum information theory tells us the bits are qubits. The black hole paradox is a crisis that arises because information, the bit, seems to be threatened. Life is a process that has learned to store and replicate the bit. Consciousness might be what it feels like to be a certain complex arrangement of bits. This is the ultimate paradigm shift. It asks us to stop thinking about the universe as a vast, empty space filled with tiny bits of matter. Instead, we should think of it as a vast, interconnected information processing system. The physical world is a representation, an output. The fundamental reality is the bit, the question, the answer. This is a daunting and exhilarating idea. It means that the universe is not a cold, meaningless machine. It is a system that is fundamentally about meaning, about information. It suggests that at the bottom of it all, there is not a particle, not a string, not a field, but a logical principle. The existence of the physical world, the it, is contingent on the existence of the informational world, the bit. The deepest truth of reality might not be found in an equation of motion, but in a simple, profound statement. There is no it without bit.